So let me just quickly touch upon the ionic equilibrium bits which we had discussed in the previous class here. So effectively we ended up having a discussion on different types of salts over here. So when it comes to salt of strong acid, strong base, you're going to be having pH being equal to 7. Salt of weak acid, strong base, you're going to be having pH being calculatable very easily. If it is like a weak acid, strong base like CH3COH and NaOH, salt is CH3CO minus Na plus. So we end up having in this particular case here that kind of a solution over there. The CH3CO minus is the main component because Na plus is going to be spectator ion. CH3CO minus is conjugate base, so its Kb will be Kw by Ka, and the value works out like this, which is less than 10 power minus 3. Less than 10 power minus 3 means all the equations apply straight away, so we can use that straight away. Kb is going to be this, and we end up having this entire thing being the pH of that solution over here. Now in this case it is not really going to be pH, it will be pOH actually, because the pOH is what is going to be taken into account in each of these cases over here. Okay, so what is meant by hydrolysis here? Hydrolysis is basically going to be nothing but the reaction of the CH3CO minus in water in this case here, or with water in this particular case here. So this is a conjugate base, so it reacts as a base with water, meaning this hydrolysis constant is nothing but Kb for this particular expression over here. So for this expression, equilibrium constant is going to be Kb for the conjugate base, which is nothing but Kw by Ka. And of course the alpha which we had over here, which is square root of Kv by C, is for the hydrolysis reaction, which is this reaction. So for that reaction we have got alpha also done. And same type of logic we can then apply for salt of weak base and strong acid, NH4Cl, NH4 plus and Cl minus over here. We are going to be having in this particular case here NH4 plus and Cl minus, concentration being C and C. So we are going to be having the NH4 plus ion will be the one which is going to be reacting with water here. What is it going to be reacting as? It is a conjugate acid of a weak base. So this fellow behaves as an acid with water in this particular scenario here. What is going to be the equilibrium reaction here? This is going to be called as a hydrolysis reaction. Why is it called hydrolysis? Because technically we are having bonds changing in water here. So this is going to be a hydrolysis reaction. So you're going to be having, what is this effective reaction here? You're going to be having this being something where the ammonium ion behaves as a conjugate acid. So it's going to be nothing but Ka for the conjugate acid is going to be the hydrolysis constant here. Ka for conjugate acid is Kw by Kb, quite clearly here. So Kh is going to be hydrolysis of this particular salt over here. That Kh is nothing but Ka for ammonium ion, which in turn is nothing but Kw by Kb. So from here we will end up having this value working out as 5 into 10 power minus 10 approximately. Again this is going to be less than 10 power minus 3, meaning all three of these standard equations are going to be applicable here. So alpha for this works out as square root of Ka by C, pH is half into pKa minus log C, and concentration of H plus is square root of Ka into C. Now, so we end up having this becoming the scenario here. pH of a salt of weak base strong acid works out as half into pKw minus pKb minus log C. Now after this we directly went into understanding how a titration works. So from the point of view of titration over here, we started analyzing what is going to be an acid-base titration. And more specifically, I started off with the discussion on what is going to be a strong acid, strong base titration. This is called as a strong acid, strong base titration. Pay attention here, we are using what over here? We are considering HCl and NaOH. So what is meant by a titration? In a titration, we are going to be having a beaker like this, which is going to be taken, and in this beaker over here you are going to be having some kind of a solution of acid or base. In this case, since we are using acid base titration here, so we are going to be considering that type of cases. So in this I am going to be taking 50 ml of 0.1 molar HCl. Okay, and what am I going to be doing? I am going to be adding NaOH to it drop wise in this particular case here. And this NaOH which I am going to be adding drop wise over here, what is going to be the scenario over here? I am going to be adding 0.1 molar concentration sodium hydroxide drop by drop to this particular HCl solution. So when I am going to be doing that, what am I going to be doing over here? I am going to be having something called as an indicator being used. Why do I need an indicator? to tell me if the reaction is completed or not, because my HCl solution is also clear solution, my NaOH solution also clear solution, NaCl solution is also clear solution. So what is the reaction will,
Clear with
IS?
I to the I clear solution.
Sorry, Kana? No, not to the
Is
I.
it?
They are clear solutions. When I am considering HCl solution or NaOH solution or sodium chloride solution or sugar solution, they are all going to be nice, clean, clear solutions, no color. Alright, so that is the reality
Yes.
there. So when you're going to be having this kind of a solution here, the reaction which is supposed to be happening is HCl and NaOH are reacting to give me NaCl and H2O. Correct? But if this is also clear solution, this is also clear solution, this is also clear solution, this is also clear, I can't find out if there is anything happening at all, or if my reaction is completed, has it
That's
started.
why you add indicator color.
Correct, yes, that is why we are going to be adding an indicator in this case here. What is this indicator going to be doing? The indicator will have two different colors seen for it in two different mediums. The indicator in this case which I am using over here is called phenolphthalein, abbreviated as HPH over here. So when I'm going to be having the solution being acidic, the indicator will be making sure that solution is colorless. If the solution is basic, then we'll be seeing a nice pink color solution in that particular case here, clearly telling us that the solution is now pink in color. That means the solution is basic. That means there is extra base present. So in this case, what am I starting with? I am starting with extra acid over here. So this is extra acid in this case here, correct? So I am starting
Yes.
off with extra acid over here, and I am adding very tiny amounts of base very slowly to it. So from extra acid, initially extra acid will be colorless, it will go into extra base over there. That means if it is going from extra acid to extra base, well, the extra acid to extra base is not HCl to NaCl as I showed there. Extra acid to extra base is from here to here. So first it will go from here to here, and then from here to the extra NaOH over here. It cannot go directly to extra NaOH. So first the HCl will get neutralized and become NaCl, and then the NaCl will end up having a little bit of extra NaOH present in it. So let's now start analyzing what we have done over here. We started finding out stoichiometry wise what is happening at different amounts of NaOH added. So at starting, this was going to be 0 ml of NaOH added over here. So when 0 ml of NaOH is added there, I am going to be having 5 millimoles of HCl. I am going to be of course having concentration as simply what to say 0.1 molar HCl. So pH is going to be equal to 1. So if I am going to be having 0 ml of NaOH added, so pH at 0 ml, this is going to be equal to 1, because you're going to be having H plus concentration being equal to 10 power minus 1, and you're going to be having 5 millimoles of it in solution. No NaOH has been added, so straight away pH is equal to 1. When you're going to be having a solution which is going to be let me get the exact values this time instead of spending too much time thinking. If I'm going to be having 5 ml, I mean 5, what to say, 10 ml being added over here. So the second case we are going to be considering is 10 ml in this particular case here. So if I'm going to be having 10 ml of NaOH added over here. So if I'm adding 10 ml of NaOH, what is going to be happening? We end up having 1 millimole of NaOH added and 5 millimoles of HCl is still present. These two will react with each other. When they end up reacting with each other, what do I end up having? I have the NaOH being the limiting reagent over here. So the limiting reagent is fully consumed, it becomes 0. The 5 millimoles of HCl becomes 4 millimoles of HCl. So I am going to be having this 4 millimoles of HCl is now present in a total volume of 60 ml. Why 60? Because this is 10 ml and 50 ml of HCl is already present in the solution here. So what do? We find out what is the concentration of HCl left over here. So the concentration of HCl left over in this particular case here works out as 4 by 60, which is 1 by 15. So that concentration of HCl left over is the same as concentration of H plus, because HCl is a strong acid, it will dissociate. Yes,
Hey, what?
the concentration of HCl left over is going to be number of millimoles left over divided by volume total. So millimoles left over is 4, volume total is 60. Correct? Yes or no?
Yes.
So 1 by 15 is going to be the concentration over here. that concentration of HCl left over is the same as my concentration of H plus left over here. Why? Because HCl is a strong acid, it will dissociate completely. So we are going to be having pH being equal to minus log of 15 over here, which is log 3 plus log 5, which works out as 0.4771 plus 0.6990, which we can calculate and get the value as 1.1761. Okay, so this is my pH at 10 ml.
Yes.
So we are going to be, I'll put that data also down over here. So pH at 10 ml is going to be equal to 1.1761. Okay, next up, we are going to be looking at 40 ml case over here. So what is this 40 ml case in this scenario over here? You're going to be having 40 ml of NaOH added. Now you are actually going to be having 4 millimoles of NaOH. We are still going to be having, what to say, NaOH as the limiting reagent, so it gets completely consumed. So I'll have 4 becoming 0. So 5 millimoles of HCl will now become 1 millimole of HCl. So we end up having in this scenario here, NaCl is going to be produced, which is going to be 4 millimoles over here. And we're going to be having volume total in this particular case being 90 ml. Why? Because we have added 40 ml of NaOH over here, so we're going to be having 50 plus 40 working out as 90 ml in this particular scenario here. So we'll be having concentration of HCl and H plus are both the same, 1 millimole left over, 90 ml, so 1 by 90 in this particular case here. So pH is equal to log of 90 in this particular case here, which works out as 1 plus log, 2 log 3. Let me do that calculation. 0.4771 into 2, so 0.9542. So in this particular case here, this value works out as pH at 40 ml, which is going to be equal to 1.9542. So as you can see here, what is happening over here, pH at 0 ml was 1, pH at 10 ml is 1.1761, and pH at 40 ml is 1.9542. So we're going to be having in this particular case here a proper increase is seen over here, but it is going from 1 to 1.9542 in 40 ml. Okay, so next up, let us start looking for 49 ml case here. 49 ml, what is going to be happening? pH works out as 3 over here. Why? Because only 0.1 millimoles is left over in 99 ml. I'm going to take it as approximately 100 ml. So 0.1 by 100, it works out as 10 power minus 3. So pH is going to be approximately equal to 3. At 50 ml, what is going to be happening? There is no HCl or no NaOH left over. Both of them are perfectly consumed. Only NaCl is present. So when NaCl is present, it is a salt of strong acid, strong base. pH is going to be nicely equal to 7. It is going to be neutral. Next up, pH at 51 ml of NaOH added here. What is going to be happening in that case? So we end up having 0.1 millimoles of NaOH is going to be there in excess. It is going to be present in 101 ml of solution. So we can approximately take it as 100 ml. So we end up having OH minus concentration being now 10 power minus 3 in this particular case here. Which means POH is 3, which translates into pH being equal to 11 at 51 ml added. At 60 ml, we end up having a similar case here. We end up having POH being less than 12 in this particular case here. Slightly less than 12. This is basically our calculation over here, which I have shown you in this particular case here. So it's 1 by 110, so it is pH which is going to be equal to 14 minus log 110. Now, what is the next thing we did? We looked at how to plot a graph in that particular scenario here, when you're going to be having a graph being plotted for each of the points here. So this is 0 ml, this is 40 ml, 49 ml, 50 ml, 51 ml, and this is going to be 60 ml. So we join all of these guys and we end up having a graph like this. So this graph, the key interesting thing to pay attention to is it is going to be something where there is a sudden jump and a very steep increase in the pH over here. Over how much volume? From 49 ml to 51 ml in the space of 2 ml. There is going to be a huge change in pH. Whereas from 0 ml to 49 ml, the entire pH over there changed by only 2. From 1, it went to 3 in the space of 49 ml. Alright, it only changed from 1 to 3. Whereas in the space of 2 ml, it suddenly jumped up and changed by 8. So it went from 3 to 11 in the space of just 2 ml. Whereas in the space of 1 to 49 ml, in that entire region, you are going to be having pH change being 2. So the key idea to understand over here is, when you are having a strong acid, strong base titration, This is a strong acid, strong base titration. You're going to be having a sudden jump or a sharp jump or a sharp fall in the particular titration over there. So if it is going to be HCl in the beaker and then you're adding NaOH, you have a sharp jump from pH equal to 3 to pH equal to 11. So what exactly happened over here? We ended up having in this particular case here from 0 to 49 ml. We had pH change from 1 to 3. That is all the change was from 0 to 49 ml. 49 to 51 ml, we end up having pH changes, pH sharp increase, sharp jump.
Yes,
And
sir.
this sharp jump in the pH over here is going to be from what to what? This is going to be from 3 till 11. And lastly, you're going to be having 51 ml to plus 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 plus. pH changes slowly again. So the pH change will be very very slow in this particular case here, not much of a change over here. And again, it will be something from 11 till say 12 point dot dot. It will not go much beyond that. Why? Because the maximum it can go is NaOH is 0.1 molar. Correct? Because yeah, I'm adding only 0.1 molar NaOH. That means the pH can maximum go till only 13. But it doesn't go till 13. Why? Because there is always extra 50 ml left over. Alright. So 50 ml, extra
Yes.
100 ml left over. Because my NaOH started increasing only after the what to say HCl was completely no only after the HCl was completely neutralized. So to completely neutralize 50 ml, we neutralized 50 ml of 0.1 molar HCl, correct? And we neutralized it with 0.1 molar NaOH. So the neutralization itself needed 100 ml. So that 100 ml is going to always be extra. So it's always going to be going from 11 till 12 point something only. How much ever NaOH you add. It will not hit 13, it cannot go above 13. Do you understand what I
Why,
mean?
sir?
Think in this particular case, what is the NaOH which is being added? The NaOH which is going to be added is zero point 0.1
Oh,
molar. So maximum pH possible is for pure NaOH, correct?
yes, sir.
pOH is going to be 1. If pOH is 1, what is pH? 13. So maximum pH possible is 13. So max pH possible for pure NaOH solution, which is 0.1 molar, will be 13. In this case, neutralization needed what? Neutralization is pH equal to 7, correct? So that needed 50 ml of 0.1 molar NaOH added, correct?
Yes, sir.
But there was also 50 ml of 0.1
Sir,
molar
made
HC.
something by plotting graphs like this.
Huh, sorry? What did you ask, Anna?
Sir, I made something to plot graphs like this.
See, I am not going to be naming something because you're going to be having the next part over here requiring me to teach something after this. Alright, and there will
No,
be
sir, I
new. Yes.
coded that using AI.
No, we are not going to waste time with nonsense. That is not what chemistry is about right now. You want to just plot a graph, you do that. I have no problem with that. Not in my class thing. You said your maths teacher anyway likes doing this or he has shown you how to plot graphs. Maths is about that only. Try it out in maths class, not in my class. Mine is not
I
mathematics, mine is
showed to
chemistry.
math, sir, on.
Mine is chemistry. We are going to discuss chemistry. Alright, we will not spend time on randomly plotting graphs just because it is more fun. I'm not denying it is not fun. I'm saying it is fun. But
No, like the graph in chemistry is a plot, right?
I understand, Ra, but to understand graphs in chemistry, you need to understand a lot of theory. Without doing the theory, you cannot understand any graph
Then
in
you can
chemistry.
explain me using this.
No, it is not something that straightforward. All right.
Why?
I am not going to discuss that right now. We'll finish this once I am done with, once I am thoroughly clear that you have understood things over here, then we'll go for the next theory, then we will see. Because if you want to check out the graphs, go check it out in that other senior students discussion which I have posted on YouTube. That will be very convenient. I think I already shared my channel with you. You can go check it out over there. It should be there available in that. But simple truth is that is also something where I have not discussed it fully. Maybe I'll put up one separate titration thing separately. What have you just sent me, Noda? Master March grapher. Okay, I don't really care. I'm not going to be interested. That doesn't
That
matter to me.
liquid.
I am not interested. I already told you that is math. That is not chemistry. I am not interested. Maybe after we are done with what we are doing, maybe we'll look at it that time. Not right now. No more distractions for a while. I have not yet even started off with what we need to start off with today. So no distractions. Pay attention. So in this particular case here, my 50 ml of NaOH and 50 ml of HCl are used up in the neutralization process itself. This is going to be 100 ml of NaCl present. Point 1 is not going to be the concentration now. Find the concentration of NaCl. That is a question which I want you to try out sometime for this particular
Yes.
case. So NaCl concentration, find it. What is the number of millimoles of NaCl which will be produced? Think in these places where we discussed. If I have say 5 here, if I have say 5 millimoles of NaOH and 5 millimoles of HCl, both will become 0. How many
Yes.
millimoles of NaCl will be produced?
My
5. And that will be in how much volume?
100.
Good. So you're going to be having 5 millimoles of NaCl divided by 100 ml. So that works out as 0. What to say, 0.05 moles per liter. So this is going to be the concentration in this particular case here of NaCl over here. And of course pH is going to be equal to 7. So I am going to be having extra NaOH coming up only after this extra 100 ml is always present. So I will never have pH of the solution on adding the 0.1 molar NaOH ever reaching this number 13. So it will not reach that 13. So it will always be 12 point something. Alright. So from 11 it will go up to 12 point something regardless of how much NaOH you end up adding in. Alright, you can add as many ml of extra NaOH, it will never reach 13. It will always be something from 11 to 12 point whatever only. 11, when is it 11? At 51 ml, it is going to be approximately equal to 11. It will be slightly, what to say, less than 11, but that's okay. So 11 till whatever you are going to be having, that is effectively what it is going to be till the end over there. That is the idea in this strong acid, strong base titration. So
Yes.
now the next piece over here is to understand how the indicator works over here. The indicator in this particular case, phenolphthalein as the indicator, works like this. We are going to be having the range of phenolphthalein. Every indicator will have what is called as an indicator range. In this case, the range of phenolphthalein,
What? Indicate the range?
pay attention. I discussed this obviously in the previous class itself. That means you have not read this at all. So now keep quiet and listen. So
Yes.
if I am going to be considering an indicator here like phenolphthalein, there is always going to be something called as a range. That indicator range over here is called as 8 to 10, or for phenolphthalein the range is 8 to 10. What does the range mean? How do you understand the range? The range is to be understood like this. It means that above a pH of 10. So for phenolphthalein the range is 8 to 10. So it means if the range is 8 to 10, between 8 to 10 it does not work. Why does it not work between 8 to 10? Because our eyes cannot differentiate colors in that range over there. Because you are going to.
Oh,
Alright, so the range basically for indicator is not the range where it works. It is a range where it does not work. So
what?
between, yes, 8 to 10 is the range for phenolphthalein. Now between pH 8 to 10, it doesn't work. So above pH of 10, it is going to be showing a pink color. Below pH of 8, it will show a colorless solution. So the range is going to be, if I put say 8 to 10 as a range, this side and this side it will work. The middle part it doesn't work. That is how the indicator's range actually works. So in this particular case here, below pH of 8, it is going to be colorless. Above a pH of 10, it is going to be pink in solution, pink in color in this particular case here. Between this, it doesn't work. When I say it doesn't work, what does it really mean? It means our eyes cannot differentiate the color between
We
both.
can't see.
Yeah, no, we can see, but if I see some white light and then look at the solution, it look colorless. If I see some
What?
pink color, yeah, basically our eyes will basically play tricks on us. Effectively, if I'm having that solution, if I have a solution pH between 8 to 10, phenolphthalein is there. If I look at something which is going to be like say bright white color light and then look at it, look colorless. If I look at some pink
Yeah.
color light and then look at it, it might look pink. Or it could be opposite. So it depends, what is it, terrifyingly. So usually when I'm using phenolphthalein as indicator, what should I make sure does not happen? I should make sure the solution is never going to be having a pH of between 8 to 10. Alright, so the idea here is, let me put it out over here, to use phenolphthalein as indicator. What is the range for this? Range is going to be 8 to 10. What must I absolutely do over here? Solution should never have pH between 8 to 10. In that particular case, I can use it. Alright, if my solution never ever ends up having a pH between 8 to 10, it can skip through that and go up, no problem. But at any point in time, it should never have a pH of 8 to 10. In this strong acid, strong base titration, what happened over here? At 50 ml, we had pH being equal to 7. At 51 ml, I ended up having pH being equal to 11. So as you can see here, it never touches that range of 8 to 10 over here. It just jumps straight through that range. It doesn't touch that particular part at all. That is the key thing about how to use an indicator. When you know the range of the indicator, you can decide what is the scenario in that particular case here. Next thing I'm going to be mentioning over here is, if I'm going to be having, say, a different indicator. There's another type of indicator also which we can use over here, which is called as methyl orange. This is another indicator. Usually this indicator I prefer using the abbreviation as MEOR. Either capital R or small r, I don't really care. Sometimes I'll put small, sometimes I'll put capital. Methyl orange, basically it's just an abbreviation. So this methyl orange over here, the range for this is going to be 3 to 5. What does this mean? This means below 3 there will be color number 1, above 5 it will be different color. Both are going to be two different colors. One of them is going to be red, the other one is going to be yellow for methyl orange over here. So when you're going to be having methyl orange here, obviously the orange there. What is the idea there? When you mix the red and the yellow properly, if it's in that between part over there, it will look orangish. If it looks orangish, we can't tell for sure whether it is yellow or whether it is
Oh,
red.
that is why they named it methyl orange.
Mostly, I'm not 100% sure, but there's a good chance that is the reason why it is called methyl orange. But ultimately the game is going to be, if you want to use methyl orange as indicator, what should you do? The solution should never have a pH between 3 to 5. Okay? If it goes into that range, we can't differentiate what is what. We cannot tell anything there. So it should avoid that range of 3 to 5. Now I have a question here. Can I use methyl orange as indicator for strong acid, strong base titration?
Can you use methyl oranges?
Can I use, that is my question here is, can we use methyl orange?
What?
Strong acid, strong base titration. That's the only one we have done, na? Can we use MEOR for strong acid, strong base titration?
Oh, sir.
You think and tell da. What is this nonsense where you are
Sir,
basically
three
guessing?
strong acid only, right, sir?
You think and tell properly. I have
Sir,
given
then
you,
yes, yes.
I don't know. You'll have to give me a reason if you're saying yes or no. Because your
Sir,
first answer
because
was nonsense.
strong acids like the range is like 1230.
1230. What was the pH at 49 ml we had? It was 3. Approximately 3.
Yes, sir.
So at each of those cases, it never went above 3. That is the key point I wanted to hear. What did I want to hear? I wanted you to explain to me that there is no point at all where the pH is going to be between 3 to 5. That is at
Yes.
49 ml. What is the pH over there? At 49 ml, pH is 3. At 50 ml, what happens to the pH over there? pH is going to be equal to 7. So there is no point at all where the pH is ever between 3 to 5. So pH of solution is
Alright.
yes,
Then nothing. I was just going to repeat the same thing you said.
cool, is never between 3 to 5. Hence, we definitely can use methyl orange for strong acid, strong base titration. So, both phenolphthalein or methyl orange, we can use any one of the two of them, are good indicators and work for strong acid, strong base titration. They work perfectly well in these cases over here. Okay, now we are going to be I'm going to be discussing a couple of other things now, but I'm going to be giving you information now. Alright? This is going to be information. If you want to do the mathematics, we'll have to sit and do a lot more theory. So I'm not sure if that theory is going to be necessary for your what to say school syllabus at this level, because usually this is going to be higher end stuff, which is going to be like advanced level concepts, which will be useful for what to say actual 11th and 12th standard kids. But you are in a proper extreme fast track even though you are in class 8. So yeah, I still would not want to guess what they will do in your school, so I'm not going to be giving you the logic for it. I'm going to give them to you as information now. So I want you to start paying attention carefully now. So strong acid, strong base titration. We ended up having the jump or fall was from 3 to 11. So it was either what to say jump or it is going to be a fall. So sharp jump or sharp fall. What does that really mean? That means we are going
You
to be
wanna go
having.
down fast or go up fast?
No, that is correct. That part is correct. But what does that really translate to from our indicator nonsense we have been discussing? The pH is never between 3 to 11 for a long, for any meaningful amount of volume. That is the key point to understand here. So, what is the extra bit which we can now understand or extrapolate from here? Implies if indicator range fits in the sharp jump or fall, implies indicator can be used for that particular titration. So, in this
Yes.
case here, you understood the meaning over here. Phenolphtalene's range is what? Phenolphthalein range is 8 to 10. 8 to 10 is in between that 3 to 11. So indicator can be used. Methyl orange, what is the range? That is going to be having a range of 3 to 5. So we are going to be having 3 to 5 is also perfectly in between 3 to 11. So what is this jump or fall which we have for this guy? This is 3 to 11. So 3 to 11 is going to be something which is a larger set where phenolphthalene's range and methyl orange's range are both part of the subset of that thing. So both of these indicators can be used for a strong acid, strong base titration. You understood this piece of theory here?
Yes, sir.
Now we will go to the information parts over here, which are going to be the next parts over here. Okay, if I'm going to be looking at a titration of strong acid, strong base, we ended up having it like this. Now we have learnt about weak acids, weak bases also. So let's try to see what their scenarios are going to be. I am not going to show you the math here. If you want to do the math, you'll have to learn the next concept which I'll be discussing after this, and then apply the same type of mathematics as we have done till now. Combine it with the previous concept. Previous concept now. Let me give you an example of this. You'll understand immediately that where it will lead to. So if we are looking at a strong acid, weak base titration. Okay, yeah. So strong
Yes.
acid, weak base now. Let's take examples here. I'm going to be looking at HCl and ammonium hydroxide. So let's say 50 ml and zero point 0.1 molar HCl. And I'm going to be adding 0.1 molar ammonium hydroxide dropwise. Okay, so if I'm doing this titration, what does that mean? I'm going to be having HCl in a beaker. I'm going to be adding ammonium hydroxide to it drop by drop slowly. What is going to be happening in this particular case is, I'm not going to discuss this fully, I'm just going to give you information, so pay attention properly. The sharp jump, there will be a sharp jump in this also. Alright, sharp jump or sharp fall will be there. So when will there be a sharp jump? The sharp jump is if HCl is in beaker
Yes, sir.
and ammonia added dropwise. And this is going to be for vice versa. Vice versa of what? Vice versa of this. Okay. So in this case, you're going to be having a sharp jump or sharp fall over here also appearing. But this sharp jump or sharp fall in this particular case is going to be from 3 to 8. Alright. It is not going to be beyond a level over here. It is going to be only from 3 to 8. So the sharp jump or sharp fall has changed over here completely. So for strong acid, weak base titration, what do I mean by this over here? If I am drawing a graph, how will that graph look like? So if I am plotting a graph like this, alright, so I will now have in this particular case also something like this happening. It's a very badly drawn graph, but yeah. So I'll have something like this happening in this case also. But in this particular case, it will be same type of thing. As in, over here, I will end up having this as say 0.1. Let's call this as location 1. Let's call this as location number 2. Not so much, I'll just put it as location number 2 here. And this is going to be location number 3. So what is going to be happening over here is this location number 1 is going to be say 49 ml. pH will be still approximately equal to 3. And we'll end up having at location number 3, location number 2 will be 50 ml and location number 3 will be 51 ml. But at location number 3, I will have pH as approximately equal to 8. I will not have too much over there. I will have the pH being just above 7, approximately equal to 8. So this sudden jump which is going to be happening, it is going to be from pH equal to 3 to pH equal to 8. It will not be beyond that. That is basically the idea in this particular case here. This is going to be the scenario for a strong acid weak base titration. Now next up, if I was going to be having a strong base weak acid titration. Alright, so if I am going to be having a strong base and a weak acid titration, in this particular case, what is going to be the scenario here? So you can think of it as, instead of 3 to 8 over here, approximately 3 to 9 is also acceptable. So you can think of it as 3 to 8.5 approximately. Maximum. Ideally 3 to 8 is fine, because beyond that it is not going to be feasible. 3 to 8 is actually fine. Keep it as 3 to 8. Approximately it will be like 3 to 8.5, 3 to 8.6, 8.7. Now we'll look at the strong base weak acid titration. In this particular case here, let's take the examples here. Strong base, I'm going to be considering it typically as NaOH over here. Weak acid, I'm going to be considering it as CH3COOH zero point 0.1 molar, and NaOH is also going to be zero point 0.1 molar. In this particular case,
Yes.
what is going to be happening? Sharp jump or fall, or sharp fall. Jump is going to be from lower pH to higher pH. That means if I'm adding NaOH, there will be a jump. If I'm adding CH3COH, I'll have a fall. So in this particular case, this sharp jump or sharp fall is going to be from a different point of view. In the previous case, what happened there? It was 3 to 8. In this particular case, it is going to be 6 to 11. This is going to be a sharp jump or sharp fall, which is going to be happening in this particular case here. So this is going to be pH jump or fall.
Yes, sir.
So in this scenario here, you are going to be having this as the particular case here. So for strong acid, weak base, we ended up having the jump or fall in that particular case being 3 to 8. Over here it is now 6 to 11. Now let us try to understand which indicators work for which titration. So if I was having phenolphthalein, the range of phenolphthalein was 8 to 10, and the range of methyl orange was 3 to 5. So now the real question here is this. Let's start off with strong base and weak acid titration. The jump is going to be 6 to 11. Which among these two fit within 6 to 11? Which can be used over there? Can both of them be used?
No, sir.
Which one can I use? What is the idea?
Uh,
Huh?
Methyl orange.
I can use methyl orange. Very good answer. I expected you to give that answer. Tell me why methyl orange?
Sir,
Hmm.
wait, let me think if I give a bit wrong
Switch
answer.
your video on. You're sleeping.
I'm not sleeping, sir.
Yeah, but you are dodging. So tell me methyl orange, what is the case over here? Why methyl orange? Or
Sir, because you said strong base, strong acid.
no, I
Sir,
said strong base, weak acid.
strong base, weak acid.
Is it methyl orange in the first place?
Yes, sir.
Okay.
Sir,
Strong
because
base.
strong base means you have high pH, weak acid means
Strong.
not that.
Yeah. All of that is correct. The jump and fall is basically 6 to 11.
Yeah,
So, which one is working over here? Below 6, it is going to be one color.
yeah,
Methyl orange is only 3 to 5.
yeah.
So, everything is below 6.
Oh, so
So, what?
wait. What?
What is the idea? Pay attention here like this. So, we are going to be having it like this. Let's say I am looking at strong base, weak acid titration. Okay? Plot it on a number line. No extra funny business in your brain. Start thinking like a number line. Okay, so we are going to be having on this number line here, it is going to be from 6 to 11. So 6 to 11, this is going to be the range of that. Now indicator, what is my indicators allowed over here? I have phenolphthalein and methyl orange. So let's take methyl orange. What is the range of methyl orange? 3 to 5. So 3 to 5 now, that is going to be an indicator range over here, 3 to 5. If the indicator's box is fitting within that particular jump, then you can use that indicator. Phenolphthalein, what is the jump over there? 8 to 10, right? That is the
Yeah,
indicator range for phenolphthalein. So 8 to 10 now, that is going to be a box in between over here. Range is 8 to 10. So look over here. The phenolphthalein is perfectly fitting within this.
yeah.
So if it is fitting within that, phenolphthalein can be used. Methyl orange cannot be used here. Okay. So for strong base weak acid titration, phenolphthalein is the correct indicator. Methyl orange cannot be used.
Yes, sir.
for strong base weak acid titration. In the same way, if I am going to be considering the other one over here, let's say I am going to be considering, say, strong acid weak base titration. So if I am going to be considering a strong acid weak base titration,
Yes, sir.
what is the jump or fall for that? It is there in this page. Strong acid weak base is going to be 3 to 8 over here. So if it is going to be a 3 to 8 in this particular case here, you're going to be having 3 over here and then 8 over here. So 3 to 8 is going to
Methyl
be,
orange.
yes, correct, good. So methyl orange is going to be the one which can be used over here. So methyl orange's range is going to be nice and it will fit over here. Whereas phenolphthalein will end up being over here. So in this particular case, methyl orange can be used for the titration, whereas in the other case here, phenolphthalein worked over there. So in the strong acid weak base titration, methyl orange is the indicator.
Yes, sir.
And we are going to be having phenolphthalein does not work for this strong acid weak base titration. Lastly, when you are going to be having a weak acid weak base titration, what is going to be happening is you are going to be having a tiny bit of a jump or a fall. What is that tiny bit of a jump or fall over here? It is going to be 6 to 8. Alright, this is going to be the jump or fall in pH.
Yes, sir.
As you can see, it's a very small jump or fall on neutralization. Now, a couple of other points which I missed out on in the to mention in the revision which we just did now. When you're going to be looking at a titration curve here, there are two particular points to remember here. This particular point, which is going to be 49 ml and 50 ml here, you're going to be having 50 ml perfect neutralization happens. But at 51 ml, we are going to be seeing color of the solution as pink. So what happens is, we are going to be having two separate conditions over here. 51 ml, when the solution is going to be changing color actually, we actually stop adding NaOH. So that particular 51 ml is called end point of the titration. Whereas at 50 ml, we have perfect neutralization happening. That perfect neutralization is going to be the exact point of neutralization theoretically and via calculations, and hence that is called as equivalence point of the titration. So we have two different names over here, one called as end point and one called as equivalence point. In any good titration, what is the idea there? End point and equivalence point should be very close. I don't need them to be perfectly the same, that is not needed. I just need the end point and equivalence point to be very close to each other, and as long as we who are doing the experiment know, okay, this end point is 1 ml more than equivalence point, 1 ml less than equivalence point, then no problem. We can always subtract or add 1 drop over there and solve as we need to. So as long as when we are doing the titration,
So, if you make mistakes,
if you make mistake, you make mistake. No escapism, you have to redo. What is the mistake
whole
over here?
citation,
What?
whole citation,
Yes. What is the
what?
mistake here? What is the purpose of doing a titration? You tell me. You have to do exact, na? What is the mistake in this particular case? What kind of mistakes can happen? You tell me.
Yeah,
You
2 3
stupidly pour
drops
the
more.
entire NaOH instead of adding it drop by drop, correct? That is a mistake?
Yes, sir.
Yeah, that means you redo. No escape. The purpose of the titration is to do it carefully, slowly, accurately. If you make a mistake in the experiment, redo. No escape.
Yes, sir.
Alright, that is exactly the problem. That, see, you don't want to redo randomly, na? That is the reason why scientists made sure they did an entire experimental setup for this. They made instruments for this, where you can control properly and you can add drop by drop by drop. But if you are going to be an idiot and add fully in one shot, yeah, nobody can help you there. You'll have to redo it. And remember, redoing is not just
Sir,
waste
you
of.
said something about adding one drop back.
Yeah, that is when you know when you have added correctly. When you added one drop excess, then you are going to be having end point of titration. If you add 100 ml excess, how do you know which ml caused that color change? You understand what I'm talking about is a mistake
Yes,
over here.
sir.
If I, let's say you have added up to 40 ml and you get bored, alright, it is time wasting, it is taking so much time, I am adding so slow, let me now pour some. Done. Entire thing is wasted. Literally. So that is the idea here. When you are doing experiments, experiments need patience and care and sincerity is necessary in in doing experiments. I mentioned before that I had seen a lot of sincerity when you showed me your transformer and the arcing the thing there.
Transformer?
Chota transformer which you had already
Toyota?
acquired over there, and the arcing experiment which you showed me. But the truth over here is this, that is something where you have shown
No.
sincerity towards it and you have shown patience in learning it. You show patience in connecting the wires properly. So the idea here is patience is necessary in experimentation. If you cannot show patience, don't go for doing any experiments. Experiments are fun, but without patience, you will get no results. It is just some random fireworks type of thing. Yeah, you want to do fireworks and not really understand what's happening, no problem. Then don't call it experimenting. That is just fun.
Oh.
If you want to call it experimenting, you do it in a manner where you understand very clearly how things are working. Okay, now coming back to the idea here. So this is basically the scenario here. You're going to be having an end point and an equivalence point. The same thing applies for all of the other titrations also. Strong base, weak acid, weak base, and weak acid, weak base titration. You will have an end point and an equivalence point. The game is to have the end point and equivalence point as close to each other. And in this case here, phenolphthalein also
Oh.
does not work. Phenolphthalein does not work.
Then what if they fall?
Yes, Kana, what?
What if they're falling away?
What is there?
They are falling away.
I do not understand what you mean, Doug.
The end point and the start.
Then that is also useless titration. The idea here is if your endpoint and your equivalence point are far away, what does that mean? That means you used the wrong indicator. Correct? That is when it will be far away. Equivalence point is theoretical. Endpoint is according to the indicator, whatever it has shown us, correct?
Yes, sir.
So if endpoint and equivalence point are far away, what does that mean? That means you use the wrong indicator. So methyl orange also does not work here. So yes, what does phenolphthalein does not work, methyl orange does not work really mean over here? It basically means this end point and equivalence point are far away. That is literally what it means. Implies we have wasted time, titration information is useless.
Huh?
Yes, that is literally what it means. Titration done with wrong indicator is a waste of time.
Like,
Yes, literally what I am saying is correct. So time was wasted, you have to redo it with some other indicator. Yeah, see, just because it is wasted time doesn't mean it is completely wasted. You know now not to do that. So if you again go and do it, you have accepted कि हाँ time waste ही कर रहा हूँ चलेगा, no problem. So this is basically the idea for a weak acid weak base titration. And now we will go for one other last concept over here which I wanted to give you and which I wanted to discuss anyway. It is called as buffer solutions. Now in your basics, in your syllabus there, I don't know how much of buffer solution is going to be there, but I am not going to be discussing too much details over here. I am going to discuss only one simple type of buffer, which is usually going to be discussed as the first type of buffer in your school over there. We will only discuss that because I don't think they will do anything more than this. So we are going to be doing a buffer where we are going to be having CH3COOH in solution, which is going to be a weak acid, plus we will end up looking at salt of weak acid strong base, like say CH3COONA. So CH3CO minus Na plus. So what am I going to be having in this case here? I am going to be having a solution which contains two pieces over here. The solution contains the weak acid at concentration C1 and the salt of the weak acid strong base at concentration C2. This is basically the solution over here. Now this solution here is going to be something which acts as a buffer solution. Now let me talk about what is meant
What's
by
a
a buffer
buffer?
solution first. So what is this buffer solution, this new weird term which I am talking about over here? Buffer solution means it is a solution which resists sharp change in pH.
Yes, sir.
Okay, now let us talk about a simple case now and you will understand it better. Let's say I had 999 ml of water, pure water, and I am going to be adding 1 ml of 1 molar HCl to this. This is going to be case 1, and in case 2 I am going to be adding 1 ml of 1 molar NaOH to this.
Right, like
Yes, you are talking to who?
my mom says
Okay,
she's asking me if I have to write notes on.
okay, all right. Now, obviously, it will be nice if you write notes, but we both know you are lazy. What can I do about that?
Yes, sir.
So, I end up writing almost everything. So, pay attention now. So, 919 ml of water is going to be taken here with 1 ml of 1 molar HCl. What will be the scenario in this case one here? Pure
Very
water, what is
high.
pH by the way? Pure water, what is pH?
7.
7. Good. Next up, if I am looking at case number 1, where I have added 1 ml of 1 molar HCl, how many
To the
millimoles have I
water?
had? 1 ml of 1 molar HCl added.
To the water?
Yeah, to that 999 ml. So how many
There
millimoles? How many millimoles of HCl? Go step by
one
step. Don't jump.
1 millimole.
1 millimole. That 1 millimole is now in how much volume?
The 100 ml.
100 or 1000 or
All triple.
1000 ml. That means what is my concentration of H plus here? It is same as concentration of HCl. So it works out as 10 power minus 3. Why is it 10 power minus 3? It is 1 divided by 1000. So it is 10
Oh,
power
sir.
minus. So what is pH?
Sir, how, so what?
You did this
Sir,
calculation.
sir, sir,
Stop,
there are,
stop, stop. Don't argue now. Stop. Listen now. 1 ml of 1 molar
yeah, ma'am.
HCl.
Yeah, 10 per minus, yeah.
So you understood clearly?
Yes, sir.
So 1 millimole of HCl is extra and the total volume is 1000 ml. So concentration of HCl is strong acid, so it's same as concentration of H plus. It is 1 by 1000, so it is 10 power minus 3.
Yes,
You
sir.
just had to pay attention to your own words which you said 20 seconds ago instead of randomly jumping around in the brain. So pH is going to be equal to 3 in this case here. So what has happened over here? On adding 1 drop of strong acid, what happened to pH? pH changed from 7 to 3. Sharp abrupt change of 7 to 3.
Sir, grapes are so acidic, sir.
Grapes contain citric acid probably, da.
Sir,
Grapes are a
I
citrus
ate
fruit,
them
na.
and so hard, and my whole hands are sticky.
That is different. Hand stinking is not because of the acidic content over there. That's because of the sugar juice over there, probably more. Anyway, now 1 ml of 1 molar NaOH. Let's look at this now. If I'm adding 1 drop of 1 molar NaOH over there, that is going to be doing what? Same thing. OH minus concentration will be equal to 3. Meaning we'll have, see, OH minus concentration will be equal to 10 power minus 3, which means we'll end up having POH being equal to 3, meaning pH will be equal to 11 in this particular case here. So in this particular case here, what has happened here? We have had a sharp change from 7 to 11. So again, you are going to be having a sharp change on adding 1 drop of NaOH over here. So the idea here is this: normal solutions, what happens to these normal solutions? They cannot and do not resist the change in pH or sharp change in pH. So when will this sharp change in pH be seen? This sharp change in pH is seen on adding,
Titration.
no, not titration. What did I talk titration here? Did I talk titration here? I did not talk titration. Sharp change in pH is not just titration.
Yes,
Okay.
sir.
So don't jump to conclusions. Just because you have learned something doesn't mean that has to be the answer for sure. So on adding small amount of strong acid or strong base, you will usually have a sharp change in pH happening, or it can happen, it may
And
happen.
is it like electronics, the buffer solution?
Sorry, repeat again.
Is it buffer solution like
No,
electronics?
no, no. We are not going to be randomly
In
talking about.
electronics, you
Stop,
have
stop, stop,
buffers.
stop, stop. Don't jump to nonsense. You are trying to connect things which you have not even learnt to stuff which you don't even know.
I
Okay?
learned, sir,
No,
buffer
no, 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 no. Don't do this.
capacitor.
Stop, stop. Don't do this. You are in 8th standard. You make the wrong connections in your brain. You will make the wrong logic up in yourself. And that will continue till your end. No, I am not going
Till
to
the
allow that.
moment I say a word,
I
you'll
am not
stop,
going to
stop,
allow
stop.
you to make up nonsense about things which you have not even learnt. Have you learned buffer solution? No. Have I finished buffer solution? No. I have just introduced it. So no assumptions now. You will
Not
not.
saying buffer solutions, I'm talking about
I am
buffers
telling
in
you no
electronics.
assumptions. I don't want any question on buffer solution now. If you are asking me a question on buffer solution, that means you think you know something. No, you don't know anything. I am clearly telling you,
I'm
you don't
saying in
know.
electronics,
See, what are you talking about there? Tell me what you mentioned there. Do you
buffer
know that?
capacitors.
Is that anything related to this? Do you ever use a solution in that? Have you seen any
Kind of
liquid? Have
they
you ever seen any liquid in that setup which you have? Did
said
you have a
the
liquid
damn
solution there?
said the damn sharp changes in signals.
That is a signal. Is that anything to do with what we are doing over here? We are doing
No,
solutions? Do you ever have a solution over there?
no,
Then does it have anything to do with this?
no,
Then why are you trying to needlessly connect nonsense?
you both have the name buffering.
No, both. There is no name there. That buffer means there is going to. What does buffer mean? This is called buffer solution. I was very clear about solution. What does buffer mean then? Solution which is going to be resisting change in pH is this. Buffer means something which is not changing. Avladhan. That is an English term.
No,
Okay, that has nothing.
no,
Yes, that is an English term.
why no?
Something doesn't change over there. Something which you are measuring doesn't change
Sir,
so
you
much.
said no, sir.
Ah, yes.
Said no.
Ah, yes.
So you're like no.
I didn't understand. I might have used some random language word, doesn't matter. But effectively, the idea
So
there
what
is,
is that? Tamil?
yeah, mostly. If I use some word which you didn't understand, it is mostly Tamil. So, yeah, it might be Hindi, but I think you recognize Hindi anyway. You're in Hyderabad here, you recognize Hindi. So, anyway, coming back to the point here, buffer is an English term. Alright, English, what buffer means is something which doesn't change. In this case, Whatever you are measuring doesn't change for it. That's the idea here. So if it is solution, buffer solution means it is a solution where,
Resistive solution.
yeah, it is going to be a resistive solution which is going to be resisting what? It is going to resist the actual thing which you are trying to do, which is change the pH over there. So
Yes.
buffer in what to say, a capacitance over there is going to be something which is going to be resisting the change in voltage. So for instance, if I am going to be having a capacitor hooked up to a circuit, what is a capacitor acting like? It is acting like a tiny battery pack where it is storing
Yes.
the energy over there for like a few bits of time, and then it will be able to drain it out if you cut the supply for a second, or if there's a tiny bit of a change in supply, that will then release the power. So it is
The
going to
buffer
be,
inductor also.
no, don't make up extra terms.
So there are buffer inductors.
Stop. I do not know what that is. I am talking about capacitor. Okay, you will have to think about what that is when you learn about what an inductor is properly.
I know what an inductor is. I used them
You
with
know
my
how it
son.
works.
Yes, sir.
That is all you know. You don't understand the full theory behind it. Or do you? I don't know. I have no idea at least. I don't know the
And
theory
you
behind
don't
it.
care.
No, it's not I don't care. I am not going to guess. When I don't know any basic details, I will not guess. Because if I guess randomly, what is the wrong thing which I am doing over there? I don't even know what that is supposed to be doing. If I know, then I can start understanding immediately using my common sense and logic which I built up in chemistry and make conclusions. They will be correct. But when I don't have any idea about what it is doing, I should not do any guesswork. If I do guesswork, I will make random conclusions which are wrong. I will be biased before I am even starting that thing. So, no
Chemistry sir's
conclusions, no
thinking go.
assumptions. When you don't know, you don't know. No randomly trying to think what it could mean. For instance, buffer in a capacitor sense, how what might be the terminology there? I understand that to an extent because capacitor will basically end up trying to maintain voltage. It acts like a battery pack for a few seconds or a few milliseconds. So what is it trying to do there? It will probably try to maintain the voltage without it changing too much if you are having say a fluctuation which is happening there. That
Yes,
much I
sir.
can confirm for sure. But I do not have any idea about how inductor works over there, and I am not going to take any guesswork. Honestly, I do have some idea, but I am not going to guess over here because I am not sure. So no random guessing, no random assumptions. If you find out what an inductor does, when you have found out and when you have understood, then you think with that term and then you understand it for yourself. Or you can come and explain it to me, then we will discuss. But no random nonsense.
And can I explain it to you now?
No, I do not want anything now. Now, next thing over here, we'll continue on with the chemistry. Now it is my time to keep talking for a while. You don't get to explain today now. After you have
Not today.
confirmed the, not today, not anytime soon. Because I will be asking you real
Yeah, that
questions.
memes are not
I am not
today.
interested in memes. I don't know what a meme is, Ra. Spelling of meme is what? MEMI? I don't know any spelling at all.
Me,
Or
me.
MIMI? I have no idea what meme means. I'm very innocent person, dude. I don't know anything. So I know only chemistry. We'll do some chemistry first. Okay. So in this particular case here, we are going to be having buffer solutions here. So it's going to be a weak acid, and we are going to be having salt of the weak acid and strong base over here. So we are having them at different concentrations, C1 and C2. Now this is a typical buffer solution. This mixture which we are talking about now, this mixture which contains this is going to be a typical example
So
of a
why
buffer
do they
solution.
resist again?
I am not going to explain the why part of it beyond a level now. I'm
So
just
why
going,
is it?
I'll give you the why. I'm not going, I'm telling you I won't be explaining it beyond a level because that is not necessarily going to be in your domain. Okay? So if you want to learn more
Domain
about this, go see
expansion.
the ionic equilibrium video for that senior student which I put up on YouTube. That will have a lot more detail. Alright, I am not discussing for you in your class though, because I do not think it is going to be necessary at your level. If your school is doing some funny business, then we will talk about it. So in this particular case, I'm just going
Funny
to give you a,
business.
I'm just going to give you a flat one line answer. So pay attention now, don't get distracted. So strong acid gets neutralized. If it gets neutralized, pH does not change much.
Why not, sir?
Think,
Sir,
if I have NaOH over if I had say this titration here, what was happening in this titration? From 0 to 49 ml, pH changed by much or it resisted the change in pH?
register the change in pH.
Why? Because there was excess HCl there, correct?
Yeah.
So
But the moment the
stop,
HCl
no
is
arguments.
neutralized,
I want you to listen now. You ask your question after I've given you the answer. So it has resisted the change in pH over here? Yes or no?
yes, sir.
On adding, what did it resist the change in pH? On adding NaOH, it was able to resist the change in pH, correct?
Yes,
If
yes,
I added
sir.
some HCl also, pH is not going to be changing. Same 0.1 molar, nothing will happen, pH will be approximately the same still. So whether I added a strong acid or a strong base, this solution was able to resist the change in pH for
Sir,
some
but
time.
sir,
For some,
from 49 after 49 it will
yeah,
change,
I am
right?
not denying it. That is why I was very specifically clear from 0 to 49. Na? Did I say above 49? Why are you
Sir,
asking for that? Obviously, this is not a buffer solution. But it was able to work like something which looked like a buffer solution from 0 to 49. But is it really a buffer solution? No, it is not a buffer solution. But it is able to
but a
resist.
buffer solution will also resist even after 49.
No, usually when you're going to be having a buffer solution, it doesn't do this level of what to say type of thing. It also resists only up to a particular point. But there is an extra advantage or important point for a buffer solution, which I did not want to mention here in the definition directly. It is that it is going to be something where on diluting, also pH does not change on diluting with water. In that case, pH will change when you're adding water. So on dilution also pH does not change.
Yes,
Okay, now we will come to this case. We will try to understand what is happening here and find the pH of this solution here. Because that formula is unfortunately something I have a gut feeling they will be doing in your school there. So let us now try to understand what is the solution. CH3COOH concentration is C1 and CH3CO minus Na plus concentration is C2. Now we have learnt already that this guy is an ionic salt. Right? So this dissociates nicely fully over here. So if it dissociates fully, what is going to be happening? You're going to be having CH3CO minus plus Na plus generated over here. So if I had starting concentration of this as C, these two would have been 0 and 0. Now this will become 0 over here, this will become C and C. So we'll end up having in this particular case here, CH3CO minus concentration is C and Na plus concentration is going to be C in this particular case finally. Na plus what kind of an ion is it, Ra? Do you remember?
sir. Plus
Ah, yes.
spectator ion.
Spectator ion. Good, nice. So it's going to be a spectator ion in this particular case here. So it does not affect pH.
Yes, sir.
So what is going to be affecting pH in solution now? We will have this CH3CO minus definitely affecting pH. And we also have, okay, I made a mistake here,
So
sorry.
it's all about the ion.
Yeah, not just the ions but the water also. One small mistake I have made here. The concentration of CH3CONA is C2. So this should not be C. I should write it as C2 over here. My mistake here,
C2?
sorry. I have taken this as C2, nada.
So what's a C2?
Both are there. There are two things. CH3COH is also there. CH3CO minus is also there. Solution
Yes, sir.
contains two things over here. So I am trying to find pH of solution containing both.
I did not get what you're saying.
Let's say I am having a beaker. Okay, yeah. I'm
Yeah.
going to add CH3COH C1 moles to it, and I'm also going to add CH3CONA salt C2 moles
Oh,
to it.
you're adding both.
I'm adding both.
Why is it?
Why? Why not?
What?
I am taking a case like that and I'm studying it.
Oh, without any beaker.
Now the reason is I am trying to study something new and I am telling you that this works like that. I have given you that information already.
Oh,
So now we are trying to study how to find the pH of that and why it works like that. So this is going to be something which is going to be containing both. What does it mean? We are going to be adding both to it. So solution contains both. Now we are taking a solution or a beaker, water, and we are adding both of these guys to it individually. So we are adding a weak acid and the corresponding salt or the weak acid and strong base. So in this case here, I have CH3COOH from the beginning itself present, and that guy's concentration is going to be C1. So let us now try to understand what is going to be happening in this solution here. We will have weak acid present now, we will have it having an equilibrium. So the CH3COH will be in equilibrium with H plus CH3CO minus. Correct. That equilibrium is going to be there. But in this equilibrium, what is happening? We have this as concentration C1 in the beginning. This is something which is, let's say, 0 in the beginning. And the CH3CO minus is present already from the salt over there, and its concentration is C2. So, we are now having one of the products present already in the beginning itself.
uh,
So, will forward direction happen much or will it not happen so much? We discussed one of those cases of common ion effect a while back when we discussed in the previous
a
week.
lot.
Yeah, I figured that. Where was that? Your thing in pH calculations is probably here. Huh? Okay, I can't find it now over here. Yes, this case. What is happening in this particular case here? We ended up having the concentration of HCl. There was a little bit of HCl already present and a little bit of CH3COH present over there. So we ended up having in the beginning, what did we have as the concentration of the alpha for that particular case? Alpha 1. This is the page over here. Yes, huh? So alpha 1, when you are going to be having only CH3COH present over there, we compared it with alpha 2, which is going to be when you are going to be having some amount of HCl also present over there. So when there is only CH3COH present there, we end up having in that particular case there alpha 1 was some value. If I had higher concentration of HCl, I end up having lower alpha value. Why will there be lower alpha value? Because this is going to be an equilibrium. In an equilibrium, if one of the products is already present, then you are going to be having Le Chatelier's principle happening. Meaning you will not have that much of forward direction happening, you will have lesser amount of forward direction, and hence you will end up having the amount of alpha value is going to be lower if a product is already present. You remember chemical equilibrium Le Chatelier's principle? If
Yes,
more products are present, backward direction will start happening more, correct?
yes,
Backward direction happening more is the same as forward direction happening what? Less. That is the simple principle to be looked at over here. So that logic is what we apply in this scenario here. So we are going to be having CH3COOH and you are going to be having CH3CO minus. Now the alpha for this is going to be very, very low. Equilibrium constant is of course K. So for this equation here, because product is also present, implies alpha is very low. So very, very small amount of forward direction will actually be happening. So let us say tiny bit happens. So we'll have it as C1 minus X. This will be some X. This will be some C2 plus X. Correct. But if alpha is very low, Then I can say C1 minus x over here is approximately equal to C1, and C2 plus x is approximately equal to C2, right? And equilibrium constant is Ka here. So what I can now write is this: CH3COOH is going to be in equilibrium with H plus CH3CO minus, and I am going to be having at equilibrium, what are the concentrations? I will still have this as C1 plus x, which is approximately equal to C1. Sorry, not C1 plus x here, sorry, that is a bad mistake. It is C1 minus x, which is approximately equal to C1. Here it will be C2 plus x, which is going to be approximately equal to C2. And this will be whatever concentration x over here. So if I am going to be calculating concentration of H plus, we can effectively write Ka equilibrium here, H plus into CH3COO minus divided by CH3COOH should be equal to Ka. Meaning we will now have, implies H plus is equal to Ka into CH3COOH divided by CH3CO minus concentration. Meaning effectively I can write this CH3COH is going to be nothing but concentration of weak acid,
Yes, sir.
which I am going to be abbreviating and putting as WA concentration. And this CH3CO minus is nothing but concentration of conjugate base, or we can say it is also concentration of salt in this question here. Correct? So we end up having, what is the case here? We have two things in solution, correct? Solution contains two things. What does it contain? The salt CH3CONA, and it also contains weak acid over here. So the salt is what is producing my conjugate base over here. So we can take it as conjugate base, or we can take it as salt. I would recommend you remember it as conjugate base. In your school, they will definitely give it as salt when you are being taught it first. Don't worry about it, both mean the same thing here. So from here, what will this translate into? We will now have pH being equal to minus log of H plus. So it is minus log Ka minus log of CH3COOH by CH3CO minus. So let me put it in the next page over here. So pH works out as minus log Ka minus log of CH3COOH divided by CH3CO minus. Obviously having too many negatives is not nice in an equation. It's easier to remember plus in our brains. And this minus log Ka is nothing but pKa. So P of Ka is going to be written as minus log of Ka. So we can write this as pKa plus log of, so log of A by B is going to be minus of log of B by A. So this is going to be minus of log of something, so it becomes log of CH3CO minus divided by CH3COOH. Meaning we can write pH of this buffer solution is going to be equal to pKa of weak acid plus log of CH3CO minus is going to be weak acid divided by concentration of conjugate base or salt. You can put it as either, but actually more correctly it is conjugate base. Now I am going to just give you one last thing over here explaining the Y. Now let us talk about the Y part over here. What is my solution containing now? It contains CH3COOH, some concentration C1, and it contains CH3COO minus at some concentration C2. Now let us go back to what is the buffer doing and how does the buffer basically end up working. The buffer there, how did it work, or what was the buffer? On adding a small amount of strong acid or strong base, what is going to be happening over there is you're going to be having that small amount of strong acid or strong base is not going to be changing pH much. Mute your side there, I'm getting feedback of my own voice again. So on adding a small amount of strong acid or strong base, you are going to be having not, I'm hearing too much of my own voice, dude. Mute your side, please.
Yes, sir.
So on adding a small amount of strong acid or strong base, you are not having the pH changing much. How? Because if I am adding a strong acid, if it is capable of getting neutralized or there is already some strong acid type thing present, then there is going to be not much change. Same way applies for a strong base. If I had a strong base added, it should get neutralized. That is how a buffer works. So what is the principle behind a buffer over here? A buffer solution can neutralize both strong acid and strong base in small quantities or in small amounts. If it can neutralize my strong acid or strong base in small amounts, properly neutralize it, then we call it as a buffer solution. Now, let us now consider what can neutralize it in this current solution which I have given you. So, the CH3COOH which is present over here, this fellow basically is going to be a weak acid. So, this fellow neutralizes small amount of strong base added. So if I am going to be adding a tiny bit of a strong base to this solution over here, what solution? To this solution containing both of them. Alright. If I am going to be having a solution where I am having CH3COH and I have added some salt of CH3COH like sodium acetate, both are present in the same solution. Then the weak acid part, which is my CH3COH, is going to be neutralizing small amount of strong base added to it. Of course, the next piece of data is going to be the CH3CO minus over here is going to be conjugate base, right? So this conjugate base behaves like a base or behaves similar to a weak base. Why? Because I know the Kb value for this. So if I had the Ka value for this as 10 power 2 into 10 power minus 5, the Kb value for this fellow works out as 5 into 10 power minus 10. Right, that's what we have seen in the previous calculations. Right, why? Because Kb of conjugate base is going to be equal to Kw by Ka of weak acid. So this fellow is going to be behaving in a manner similar to a weak base. What does that mean effectively? That means this neutralizes strong acid added in small amounts. So if I am going to be adding a small amount of strong acid, this fellow, the conjugate base, will neutralize it comfortably without any problems. Now you can unmute yourself. Now tell me if you have any questions. Do you understand this part which we have discussed so far?
No. Yes. I understood.
Now,
I don't think I have any doubts.
okay, but you'll have to definitely go through this once because this is going to be a little bit of a complicated piece over here. And more or less, I think this should complete off whatever is necessary for your official system of ionic equilibrium in your school. We will see a few questions from the next class onwards. I'll be discussing a few questions from the next session onwards.
Yes.
I suppose I'll see you with more ionic equilibrium then.